going to discuss several small things. The main topic that we are going to discuss is open quantum system, and that's extremely important now in quantum information theory, as I will show you that some things are known which you can treat properly, but many things are unknown, and that's the main trouble for experimentalists to do the experiment, because this is the main decoherence problem that experimentalists face. And so whether you work in with photonic systems or in massive particles, the problems remain. And so this is actually one of the probably one of the important research topics in quantum information science. So if you look at arXiv, you will see that several papers coming up every day where people talk about some noise related issues. So this was our aim, but for starting that topic, I need some prerequisites. So some of them, some of the topics I have already covered in my QIC-I course. So some people have done it, but just to revise ourselves, so today and tomorrow I am going to discuss about quantum correlations, and we will discuss only those parts which will be relevant for our discussions in the later time when we will talk about open quantum system. So the topic that so this is the main thing, as it is in the name. We will be talking about correlations which has some quantumness. So it's, in other words, it can be non-classical, you can also say, which is not classical. So there are many ways to characterize these non-classical correlations. So today, basically, we talk about the entanglements theory. So this also, I think, also has been discussed by Ujjwal, but and in the very detail we have discussed in QIC-I course. So whoever is crediting this course, so I, as I have already told Debras, that you take the assignment that I have given on entanglement theory. It's good to solve, okay? And the point is that okay, entanglement theory, talking about entanglement theory in one class is not enough, as we know that in QIC-I course probably we have several classes we have taken to really discuss about entanglement theory. But as I said, today we are going to discuss only those parts which are required for our discussions in open quantum system. Okay, so as probably everybody know in this class that okay, so there may be some references. So the best, as we know, there is a nice review article by Horodetsky's, which is if you want to also read a smaller version of entanglement theory, then also there is a chapter available written by us with Maciek and Anna Sanpeda, is this one. And also I will give you more references when we go further. So if I look in the system. So it's a, first of all, it's a property of states. So if I talk about property of states, the states can have just two parties, which we call bipartite, and also can have multipartite system. So what do I mean by that? So that means bipartite means there are the entire system consists of two parties, and so the bipartite scenario means there is a Alice and there is a Bob, and corresponding to Alice there is a Hilbert space CA, complex Hilbert space, and corresponding to Bob there is a complex Hilbert space B, and the joint system which describe the two particles can be described by the tensor product Hilbert space of Alice and Bob. And so any state or any density matrix will be we know that in general is a Hermitian operator, trace 1 and positive, and these operators belongs, the operators is defined on CA tensor product CB. So we talk about arbitrary density matrix which is defined on in this, or these operators are in complex Hilbert space CA tensor product CB, and we want to define entanglement in this scenario. So as I said that this entanglement is a property of density matrix or of quantum mechanical states. So if we, for pure states, if Alice prepares a state psi A, Bob prepares a state psi B, then the joint state looks like that, psi A tensor product psi B. So if the joint state psi AB is of the form psi A tensor product psi B, then the state is called product unentangled. And if we think about protocols, then these are the useless states that we know. On the other hand, if psi AB cannot be written as psi A tensor product psi B, then the state is entangled. And from the definition, actually you can prove, for example, that singlet states, which is consist of two spin half particles, so you can show that this psi minus cannot be written like that. So this we have done in class, so I put it as a homework, whoever wants to do, it's worth doing, that you prove from the definition that psi minus cannot be written in terms of psi A tensor product psi B. And now if I go to a mixed state, then things becomes much more complicated, because rho AB So entangled states are those states which cannot be written like that. Okay? And the separable states can always be written like that. So this is the form of the separable states, and the states which cannot be written as above are called the entangled states. Now you see,
Not equal to will be equal to, I guess.
no, I talk the left, right hand side as separable. The states which cannot be written, that's why not equal to. So are called the entangled states. Now the point here one should mention that as I have given that a singlet state or any pure state actually can be shown from the definition that that state is entangled very easily. I mean, you can check, for example, one can try to find an arbitrary 2-qubit state, which is alpha 00 say beta 11, and you can find out from the definition the conditions on alpha beta, and you can find out that what is the conditions on which the state becomes entangled. So what are the values alpha and beta should satisfy so that the phi is entangled, and just from the definition you can prove that. Okay. Now on the other hand, suppose I give you a rho AB state, and this we know this is known as the Warner state, which was by Warner has proposed, or was first probably one of the first person who discussed about the state in 1989 in Physical Review a paper. If I give you a Warner state, say for example, which is a mixture of singlet with a identity operator. Now I ask you the question that whether you will be able to prove from the definition that this state is entangled or not, then you have a hard time, because this is not at all easy. For a given a state, you have to, for mixed state I am talking, so even if it is a bipartite mixed states or bipartite density matrix, it is not at all easy to prove that this state has some separable decompositions, or it doesn't have a separable decomposition, because there can be an infinite number of decompositions, and you have to, it's not easy to prove that this state cannot be written like that for certain values of p. Okay, so this is not an easy task, and so this is probably already we see the complicacy coming in the picture from pure to an arbitrary density matrix, and that's why it's important to find out the detection or mathematical criteria to prove whether a state is entangled or not. So the definition can be easily extended to a bipartite as well as multipartite scenario, as I will show again now. Even in a multipartite scenario, you can easily define what is entanglement, but then given a state, to prove whether a state is entangled or not is not at all easy, and it's still there are several open questions still remain. So that's an important thing. Here I should also mention that this entire thing which I somehow give the definitions from mathematical definitions I have given, but you can also introduce some operations which can be called in short, I think already has been introduced in your class, called the LOCC. So L for local, O for operations, C for classical, and another C is for communications. So if you consider the definition of, or if you consider this local operation and classical communication, from operational point of view, you can also define these two, you can also define unentangled and entangled states. Okay? In particular, you can define that Alice and Bob so this can be a definition. So even if Alice and Bob are situated in two distant locations, separable states can be prepared by Alice and Bob using local operations and classical communication. On the other hand, entangled states are those states that Alice and Bob will not be able to prepare when they are situated in two distant laboratories. Okay? So to create an entangled state, two particles should interact. So usually you can think that there is a source which is sending one particle to Alice and another particle to Bob, and finally, so this is a theoretical people's entanglement. So this is the Alice and Bob share the state which is entangled. So there is a source which from where source creates an entangled state. Now source can be a parametric down converter. In case of photon, it can be a trapped ions describing certain Hamiltonian like a transverse Ising model or something, and that finally create an entangled states, send one particle to A. For massive particle it will be hard, but let's consider we know how to send, and so source sends one particle to A, another particle to B, and finally they share an entangled state, so they share a state rho AB which is entangled. So this is the one way to create an entangled states, where there is a way, or one can think that Alice has a machine to create an entangled states. Alice prepares an entangled states, keep one particle with her, sends another particle to B, and finally they share an entangled state. So this is so the LOCC or local operations and classical communication. Here one should remember that I'm not going to discuss in detail, but in case of separable states, I mean in case of PO states, actually the way I have prepared, local operations means local quantum mechanically. So here is something subscript remain, which is actually a Q. So local operations means local Q. Can you see here if I write? Sorry. So this Q is, you can think, quantum mechanically allowed operations. Okay. So this is the meaning of local operations. So as you see that Alice preparing psi A by certain operations, right? One has to do something, okay? Either you have a crystal, nonlinear crystal where you have to put laser, which actually eject a particle, or you can have some interacting thing which, or somehow you can create a photon or fermion, boson, whatever you create. And Bob also prepares this state, okay? And the joint state is a product state. And for that, actually, local operation is enough to define an unentangled state in case of pure. On the other hand, if you talk about a mixed state, then you see that we have also done a mixture. So with probability pi, where I is remaining, okay, in both the parties. So these correlations that we have built up required actually a classical communication. So I'm not going into detail, but you see that in case of mixed states, classical communication is crucial to somehow create correlations between Alice and Bob, but this correlation is different than the quantum that we are talking. It's an entirely classical correlations that Alice and Bob prepare by using this classical communication, which can be just a phone call or an email or anything which is classically possible, okay? So this is, as I said, this is a mathematical definitions, but this can be well justified from an operational perspective, like local operations and classical communication. And I think in this entire thing, that what is the take-home message is the following: that in pure states, it will be easy to prove entangled states by using just a mathematical form. On the other hand, it will not at all be easy to prove in case of mixed state. Okay. So this is the definitions. We will come back to the measure, but before that, let's discuss about the multi-party scenario. So now I add another party, which is C, and so I have to add a corresponding Hilbert space, complex Hilbert space of C. Okay, so this is my multi-party scenario. So as it is in the name, so we are talking about system now, quantum mechanical system, or their property we want to discuss, where there is multi-party, or there are more than two party that we are talking. Of course, two party is already multi-party, but here we are talking about n number of party. But let's discuss at least the three in detail, which we actually will require for our later study, and then we will go to a more party. So to multi-party, the papers that I especially feel are good is probably the one of the original paper is by, well, there are many papers, but this is by Dur, Sirac and Vidal, which actually talk in detail about a three party, which is PRA 62 0623 14. There are many, of course, as we will discuss, these things becomes extremely complicated in case of multi-party. So there are several papers. There is also a quite nice paper on hierarchy of multi-party states by Illuminati and others, which is also a physical review A, I think around 2004 by Illuminati and other people, but I do not remember what the other people. What happened? No, just tell.
Illuminati.
Illuminati is a
Controversial secret group that runs the world.
theories also. There are conspiracy theories.
Okay, so this is a Anyway, so he is Italian, nice person, and okay. So okay, so this is a physical review paper. There are other papers where also it's discussed. In case of three-party, actually, you can also look at one of, in our many papers we have also discussed in detail, at least review the thing. So the archive paper that I mentioned there in, this is the Sritama Titash paper, where also we mentioned about three-party. In a very basic way, we also discuss this bipartite, multipartite scenario. If you look at, I have written a one current science paper, which you can also look, I mean, just to be very precise way, if you want paper, want to know about this entanglement theory. Okay. Another thing I just want to mention, that whoever at least is doing crediting this course, the things that I have discussed also in QIC-I course. So I will probably write several papers, okay, in my in my class. So I really suggest, I think I have also told this to Ratul's batch and all the QIC batches that I have taught, that at least download the paper. So, okay, I do not expect that you read the paper, all the papers that I will mention. They usually count that how many papers I have mentioned. What?
So far.
70.
7 papers so far.
Today? Oh, very less. Okay, so usually I usually mention, so at least downloading help you to know the title of the paper, okay, which I am not mentioning. So I think it's worth, okay. So particularly who are crediting, as you know, I usually check laptop. So I come with the laptop with the folders. I will not check any other folders, any other things, only those where you have downloaded papers. So please come. I have checked. I mean, it's not fun, Devraj. Ask. I have checked, right? So this will be a random check. So be prepared. Okay, who are not crediting, they can also download and also can show me, okay? So that we know finally that in which chapter I have mentioned how many papers, how many I have missed, so that I can add. Okay, so let's go to a tripartite scenario. So this is the tripartite case. As you know, that this actually is a, it seems that it's very simple, because if you have a tripartite state, then Alice prepared psi A, Bob prepared psi B, and then Claire or Charu prepared psi C. Okay. So now I actually is changing to Alice to Alia, B to Broto, and C to Charu in this class. And so this state is called the fully separable, because it's actually Alice, Bob or Alia, Broto and Charu. Their particle never interact. So Alia prepares her particle in her lab, Broto prepares his particle in his lab, and Charu also prepares her particle in her lab. So they never interact, and so it's called fully separable states. Then actually things can be another type of states you can think of, which is where Alia and Broto's particle interact, create an entangled state, and but Charu's don't, and in that way you can have Alia Charu's particle can be entangled, Broto Charu's particle can be entangled. So there are 3 types of entangled in that way you can create, which actually called biseparable one. And there is a state psi ABC, which is neither fully separable nor or biseparable, and these are called the genuine multi-party entangled state or tripartite in this situation. Okay. Now again you can take as example, so you can try to prove from the definition. This is the called GHZ state. G is for Grinberger, Horn, Zeilinger states. So this actually was introduced in a different context. So try this as a homework. So I think these are all homeworks has been done by QIC-I people, but please do it because otherwise you may have a problem in final exam. Okay, so this is also again from the definition you can prove. Actually, you can also prove for n party because this has a extreme symmetries, but not all the states can be proven in this way already in multipartite pure state scenario, because you will see that there will be much more complicated states can come up. So if I now increase this Hilbert spaces to n party, so as you can see, in case of 3-party, we already have 3 categories of entangled states or unentangled states, or according to entanglement, there can be 3 types of states. One, which are fully separable, then another one is a biseparable, or you can call this bi to be 2 separable, okay, same, and then there is a genuine multipartite entangled state. So if you have a n party, so n quantum mechanical systems, then how many types of how many classifications you can make? Sorry? Why n plus 1? N. Okay, so n with a different variation, right? Because you see that this is unique, because this can be written even for n party. Now here there will be a NC2 possibilities, then NC3 and so on. So each one has a different possibilities. So given now a multipartite state, proving that is a genuine multiparty entanglement can be held. I mean, can be possible, but it it will be more and more complicated when you increase it. Okay. So if you have a n-party system, arbitrary n, then you have a fully separable state, then you have a 2 separable states, and actually you can think you can have a k separable states. What is k separable? That psi AB, say now I call A1, A2, AN, okay? So which has separable in k bipartitions. Okay, so that means say this one, okay. So this is in k partition, it is separable, and then you have a genuine multi-party entangled states which cannot be written in a n-1 separable way. So, for example, the state which is say psi n-1 entangled with psi n. Okay, this is also another kind of states which is also not genuine multi-party entangled state. So you have to check that this state cannot be written in any. So a genuine multi-party entangled states, a state is said to be genuinely multi-party entangled if it is not product in any bipartitions. So if you given a state, you make several bipartitions and you show that there exists no bipartitions in which it is product, then it is genuine multi-party entangled states. And the example of n-party again can be a GHZ state, and there is another good example which is called W state. This is also known as a decay states, which was introduced in the context of atom optics, where you have all these particles is in the ground state and one excitation, and so all the combinations of that is called the W states. You can actually have this kind of states several types. You can have two excitations, you can have half or n by 2 excitations, n by 2 in a ground state, and several such possibilities of that kind of states. Okay, and they are examples of genuine multi-party entangled states, and they have a nice properties which is different than the GHZ in some scenario. Now we will show that there are, although in case of pure states, in case of bipartite, there is a unique way to quantify entanglement, and you can find the state, or there is a unique state which actually can be called a maximally entangled state. This is no more true in case of multipartite scenario. There are several papers which claim that, so some people, initially people believed that the GHZ state has some kind of maximal entanglement or maximum quantum correlation, but there are several papers in literature where you will see that in some respect also people have claimed that W state or some other states are more powerful than GHZ state. Powerful means with respect to some quantum information protocol, with respect to some way to measure quantum correlations, which can be violation of Bell inequality, which can be a multipartite Bell inequality, bipartite Bell inequality, which can be a steering inequality, can be quantum discord, some other protocols, anything. So it's not a unique way to measure entanglement in a multipartite scenario. As we will see in our class also, it goes on, we will discuss more and more these things, and we will get more and more examples where we will see that there are non-maximally entangled state can also have a special status in a multipartite scenario. Okay, so this is actually the classification of entanglement with respect to from the definition. Now I actually need in our class the measure, so I will very briefly describe how to quantify entanglement. So there are okay, so one thing I should say that any entanglement theory actually, of course, consists of definition that we already have given. Now there are two things that comes to the mind after the definition, that given a state, we want to know whether the state is entangled or not. So this is a qualitative questions we ask that lead to the something called detection. Okay, so it actually, you experimentalists prepare certain states, tell to the people that whether the state is entangled or not. The answer in this scenario will be yes or no. Either it is entangled or not. So this is the detection method. So over the years, there are many detections method which has been discovered. One, the most common or efficient theoretical methods are partial transposition criteria. I will discuss in brief because I need it for other purpose. There are other methods. Experimentally, probably one of the successful one is the entanglement witness. There are other things like covariance criteria, realignment, several. So I'm not going to discuss. I think this we have covered in our QIC-I course, but so I am not at all going to discuss today about detection methods. If you are interested in the detection method, there is a nice review paper by Otfred Guenet, Geza taught, physics reports, possibly in 2012, but I'm not sure. One has to check. So Otfred and Geza has written one physics report, so it will be easy to find out. And so this is a nice review because they are kind of experts on detections of entanglement criteria, and especially Otfred and Geza, they are kind of experts on entanglement witness. So they have really worked closely with experimentalists to show that some states are entangled or not. So if you look at the paper by Rainer Blatt in 2008, when their group showed that the 8 ion entangled states, Otfred I think is a co-author, where he actually helped to show this that the state is entangled. So you can look on this review article if you're interested in the detection method. So this I am not going to discuss because this is beyond the scope of this course. So, but I need something which is actually the measure. So the point now is we want to fix the scale. So we know, suppose I know the detection method, that means I know the answer of yes or no, that is whether a state is entangled or not. Now the next question is to find the scale of entanglement scale we want to prepare, which can tell us how much entangled the state is. So the entanglement content of the state is the main concern, and that leads to the area called quantification of entanglement or entanglement measure. Now we have a bipartite and multipartite. So how to quantify? So first of all, bipartite also has a pure and mixed. Okay. Now in case of bipartite pure, we have quite a unique way to define or to measure entanglement or to quantify entanglement, and that can be shown to be, which again I am not showing, is the entanglement of a pure state is the von Neumann entropy of the local density matrices. So this was introduced, I mean this was proven. It's again a good paper by Bennett and others. So I don't have a exact thing, but I remember probably this was proven by Physical Review A. I think the volume is 54, and I do not remember the page number. Okay, so it's around 1997 and so on. So 1996 is the first paper of PRL paper by Bennett and others, where they have shown how to distill entanglement. I think Ujjwal has introduced distillable entanglement. And then there is a nice Physical Review A paper where they show, in case of pure states, all these things, and there are several, actually 3 papers of Bennett are important. So one I usually remember, this is possibly 54 volume, you can check. Okay, so this is by Bennett. And where it shows, now von Neumann entropy, probably you know, this is a local density matrix. Rho A is the local density matrix, von Neumann entropy is trace of rho log rho. So if I have a rho, I can write in a spectral decomposition. Then von Neumann entropy of rho, because rho is a Hermitian operator, we know that every density matrix or every Hermitian operator has a spectral decomposition, and I can write, and if you write, then this will be just like lambda I log lambda I. So if you have a singlet state, then we know that local density matrix is half I, then identity operator with half, and so the 2 eigenvalues are half and half. So if you write immediately, that is half log half log half with minus sign is immediately giving you 1. Okay? And if you have a alpha 0 0 plus beta 1 1, since 0 and 1, if you write that they are actually orthonormal, so 0 1 are orthonormal vectors, then you see that the local density matrix will be alpha square, beta square will be the eigenvalue, and so the von Neumann entropy or the entanglement of a pure state would be minus alpha square log alpha square minus beta square log beta square, immediate. Okay, so this I think you can understand. So this is a unique way to prove that the entanglement of a pure state is a von Neumann entropy of a local density matrix. One can show that the distillable entanglement of a pure state is also von Neumann entropy of local density matrix, and the entanglement cost is also the von Neumann entropy of the local density matrix. So just to remind you, distillable entanglement tells us that how many copies of the initial state you require to have a n number. So n number of copies required, arbitrary density matrix required to obtain m number of copies of singlet state. Okay, so this rate is the distillable entanglement. Entanglement cost is just opposite. So how many singlet states you require to prepare an arbitrary density matrix rho A. Okay, so this is an asymptotic definition, and you can prove that these asymptotic definitions can converge to von Neumann entropy of local density matrix. So in other words, this is just the entanglement cost of psi AB and entanglement of distillation of psi. So this is a very nice situations for bipartite case. Things are not so beautiful as we know, life are not so, and that's the probably the fun in the research. If everything is solved, then we don't have to have this class. I mean, I think that the class is to learn as well as to know that there are some chances to do research in this area. So there are many open questions. You can address one of them because they are easy. So people are trying. So we should feel that they are easy. We will be able to do it. So okay. Anyway, so now the mixed states, and things are extremely complicated, and we really hardly know computable. So the asymptotic measures, which I have just now told, distillable entanglement and entanglement cost. So for a given density matrix, hardly we know exact distillable entanglement of any density matrix. Only for few density matrices we know the exact value of distillable entanglement or entanglement cost. They actually a single paper. If you write down, if you find a distillable entanglement of a state, so this is a paper. So Riva is thinking which state I should consider so that I can write a paper. Yeah, we will discuss later which one we can address. But not at all easy, huh? Anyway, so this is not so easy. So then there are other way to, one thing I must say that since we know we know how to define or how to quantify entanglement in case of pure states. So it will be at least possible to to discuss or to define entanglement for mixed states. Whether I can compute or I will be able to compute, that's a different question. So for example, we can write that rho AB, any pure state can have a mixed state, any mixed state can have a pure state decomposition. So I can write this in terms of this. Now we know how to quantify entanglement of a pure state. So I can always write that this will be this. Okay, there is a convexity issue, but I suppose I believe that this is true. Now, so if I know this entanglement, and then we know that this Pi, because entanglement of each pure state is the von Neumann entropy of the local density matrix of all these pure states, right? So immediately we get the definition. But then what is the trouble? The trouble is there are infinite number of such decomposition exists for any arbitrary density matrix. Which one should we take? So if I talk about entanglement cost or formation, that means I need a minimum number of, I have to minimize over such decomposition, and that is exactly so you have to minimize over the decomposition, and which is not easy. You don't know which decomposition has to be taken so that the quantity is minimized. So this is the hard part. And this is not at all easy. Okay? Only for 2x2 system, compact form is known, and this is by Utter's PRL 1998, 802245. Yes. So this is the entanglement of formation paper by Utters, where he was shown that how to calculate these minimizations in case of two spin-half particles. In general, we still don't know how to calculate entanglement formations for arbitrary density matrix, even in a bipartite scenario, and that's the main problem. Now, this way, going from a pure state to mixed state is the way I define entanglement. Always for any measure of pure states can always be extended in this way to mixed state, and this extension is actually commonly known as convex roof extension. Okay, so if you know a measure of a pure state, you can always go to you can always define an entanglement measure for mixed state. Of course, the question remains whether you can calculate or not. That remains open. Okay, so that's a difficult part. I am mentioning this because this may help us to do certain issues in a multipartite scenario. So this is the scenario of mixed states, but the things are not that bad because we can define entanglement measures. So this is one way to define entanglement measure. So there is the second way which actually can be calculated, and in our class, especially when we study open quantum system, mainly we will calculate this entanglement measure. So this is logarithmic negativity introduced by Vidal and Warner in Physical Review 8. And this is probably one of the computable entanglement measure, to my knowledge, which can be computed for an arbitrary density matrices in any dimension. There is a small issues which I will discuss. So this logarithmic negativity is based on something called a detection method that I have discussed, is partial transposition. So just define what is partial transposition. Suppose you have a state rho AB. You can always write in this way, and the partial transposition of with respect to A is, as we know in case of matrix, that it will be just the transposition with respect to a single particle. Now the good thing is that these partial transpositions, after partial transposition, the positivity is no more, positivity, the state may not, or the rho AB transpose A may not remain state, so it can give a negative eigenvalue. And if rho AB transpose A give a negative eigenvalue, that means it doesn't remain a state. That is actually showing that the state is, that implies that the state rho AB is entangled. Okay? If you are interested, this was the partial transposition, was first, it was introduced by Asher Perez, 96. This criteria was shown to be a necessary and sufficient criteria by Horodetsky in Physics Letters A, 96, where they show this is a necessary if and only if criteria for 2×2 and 2×3. And this actually used a very nice theorem, mathematical theorem, to show, because this criteria can be mapped to a positive map and can be used the complete positivity, etc., which we will discuss in our open system class. So this is the partial transposition criteria. Now using this partial transposition criteria, one can define a entanglement measure which is called logarithmic negativity. To define logarithmic negativity, let us first define what is negativity. So negativity of rho AB, denoted by n of rho AB, is equal to where this we called a trace norm. And so for a Hermitian operator, the trace norm will be, this is also the, any operator it is a trace norm, but for Hermitian operator, one can show that it will be actually the sum of the absolute eigenvalues. And in case of state, that means if after partial transposition the partial transpose state remains a state, that means which is the case for separable state, then this will be just the trace of rho, and that means 1. So 1 minus 1 is 0, so it will be 0. Okay. On the other hand, if it doesn't remain a state, then this actually just the trace norm reduces to the sum of the modulus of negative eigenvalues, and so now the logarithmic negativity of rho AB is nothing but log of 2n rho AB plus 1. Now we know that this is a log of 2. 2 is the base. 2 modulus of lambda I sum plus 1, where lambda i's are negative eigenvalues of partial transposed state. Okay. Now it will be very easily checked that this, so maybe I rub this part. So here actually one should write that this is an entanglement of formation which can be computed for 2 cross 2, then 2 is logarithmic negativity which can be computed for all dimensions. Now you can easily check that for, say for example, if you take a singlet state, that means you can write in a matrix notation. So suppose this is 0, 0. So you see that this will be non-zero, this will be half. This will be your rho AB. Okay? If you take a partial transposition, this will go to here, this will go to here. Okay? That means this is the partial transpose state of the singlet state. And if you calculate the eigenvalues, the negative eigenvalue will be minus half. You can check. Okay? So that means n rho AB or log of n, so n rho AB can be written as, now in case of pure states, n rho AB is nothing but half of summation C alpha square minus 1. Now these C alphas are the Schmidt coefficients of the pure states. Now, okay, I haven't defined Schmidt coefficients, but if you know that the C alpha can be also called the eigenvalues of the squares or eigenvalues of the local density matrices of a pure state. Okay, so in case of singlet state, this C alpha is nothing but half, right? So it will be. So you can check that this will be half, and so log of 2n rho AB plus 1, which will be exactly equal to 1 for singlet state. Here also you can calculate because this is modulus of half. Okay, so negativity will be just the modulus of the negative eigenvalues. So it will be 2 into half, that is 1. 1 plus 1, 2, log 2 base 2 is 1. Okay. So in case of singlet state or any maximally entangled states, partial transpositions in case of 2 cross 2 is actually half, because this is the only negative eigenvalue that you see, and modulus of that eigenvalue, because you have to take a partial transposition, will always lead to an eigenvalue minus half. Modulus of that is half. So negativity actually is half in case of pure maximally entangled states. On the other hand, if you take a logarithmic of that, you actually take logarithmic in that way so that it scales to 1.
In the multi-parted case, you were saying that the maximally entangled states are not well
We
defined.
haven't talked about multi-party, so please stop. Let's finish bi-party. Okay, so this is the, so this can be calculated. And so in 2 cross 2 and 2 cross 3, this actually characterize properly the entanglement of a bipartite scenario. On the other hand, in a higher dimension, so maybe I rub this. So is it clear that this will be 1? It's not clear? No. So for whom it is not clear? Can you raise the hand? You. Okay. So okay, let's try once more. So you have to find out the eigenvalue, negative eigenvalue from the partial transpose state, right? You can find that this is just minus half. There are other positive eigenvalues. The only one negative eigenvalue, that is minus half. There is a beautiful paper by Anna Sanpera and others where they show that in 2 cross 2 there can be only one negative eigenvalue. Okay, but this we don't require. We can just put a brute force method, try to calculate the eigenvalue, and you find minus half. Now negativity of rho AB is sum of modulus of all the negative eigenvalues. Now there is only one eigenvalue, so it will be just half, right? And so logarithmic negativity of rho AB is log of 2 n rho plus 1. So 2 into half is 1 plus 1. So 2, that is equal to 1. Clear? So what I said that this is one way to calculate. In general, for a pure state, so if I want to calculate pure state, then negativity of a pure states can be written as where C alpha are the Schmidt coefficients or the square of the Schmidt coefficients or the square root of the eigenvalues of the local density matrices, okay, or the Schmidt coefficients, because Schmidt coefficients are the square root of the eigenvalues of the local density matrix, right? Sorry?
The minus.
Yeah. Yes. Sorry. Okay. So this is for pure state. You can show that. You check in Vidal Warner paper. It's it's very straightforward. You just write it in a Schmidt decomposition. You just apply the trace norm formula. You will get that this will be the condition. So if you have a pure state, then either you calculate partial transpositions or do that way, or you know Schmidt decomposition, then you calculate the Schmidt coefficients and you sum them, square minus 1 by 2 will be the negativity. Once you know the negativity, you can calculate the logarithmic. Okay, so this is the scenario. Now just one comment why, although I am not going into detail, but I'm running out of time.
No, 15 minutes.
When I have started?
11:30.
Yeah. Okay, good. So now the question is whether it's a good, so as I said, so I make a comment that it is a good measure in 2 cross 2 and 2 cross 3. Now why I make this comment, this I am also going beyond this class, but just for information, because as I said that in partial transposition criteria is a necessary and sufficient criteria only in 2 cross 2, 2 cross 3. Similarly, logarithmic negativity based on partial transposition criteria, and it is a good measure of to characterize entanglement. Now here this good I am also again using with a very naive sense, because good has a proper meaning in quantum information science. That also I'm not going to discuss, because the measures which can be called good has a proper definitions that we also discuss in QIC-I course, which I'm not going to discuss here. There is a beautiful paper by Horodeczki in 1999 called Limits for Entanglement Measure, which is a PRL paper in 1999, where they have proposed that a measure which should satisfy certain conditions so that the measure can be called a good entanglement measure, and that entanglement measure should lie between the distilled level entanglement and entanglement of cost. They show in that paper that asymptotic relative entropy of entanglement satisfies all the conditions, and they show that this is a good measure of entanglement. So what I talked about so many things because just to tell you that logarithmic negativity, whether satisfy all the conditions of Horodeczki's or not, we are not discussing. Okay? Actually it doesn't. So in that sense it is not that good measures, although it's an entanglement monotone, etc. But it is good because it is computable. We don't have anything in hand. Jo milta hai. It's not like that bad also, it's good. So the thing is that it's in 2x2, 2x3 properly characterized entanglement, but then it is not properly characterized entanglement for higher dimension, because in 2x4 and in more than 2x4 we know there exists a PPT states which are entangled, and they are known as bound entangled states. This is by Powell Horodeczki in PLA paper, and all the Horodeczki in PRL 98, I think it's 97. So this is the paper. There they show that there exists a positive partial transpose state which is entangled by, of course, not the partial transposition criteria, but they use something called range criteria to prove that, and they show that there exist certain states. So in 2x4 onwards, there will be some states which are entangled, but is zero if you calculate logarithmic negativity. So logarithmic negativity cannot characterize PPT bound entangled states because of its definition, because of its origin. Okay. So this I am just mentioning, it's not so important. I mean, not important, it's important, but not important in our today's class. So this actually is another beautiful area of which we now know is important. So that's the reason that I'm saying that it's not good. Now I go to a multipartite scenario. Now to discuss the multipartite scenario, one examples I want to give. So in case of multi-party, I have defined, for example, in case of three-party, we have defined that what is fully separable state, what is biseparable state, and what is genuine multi-party integral states. And we have defined it for pure states. I mean, that I did purposefully actually. Now I will actually tell you that in case of mixed states, things are very complicated. So if you have, suppose, a n-party state, the fully separable state is those states which can be written like that. Now the same problem that given a mixed states, even for two-party we cannot do. Now we are defining, I mean, definitions can always be made because this is you are free. Now the question and the top part is to prove. Okay, so given a state, whether I will be able to write the state in that form, because to write in that form means you have to actually check all the bases, right? So there can be a state, and the good example I always give in my class is this. So this actually a superposition state even in pure state, and it looks like, I mean, it is entangled, but we know that this is nothing but this. So it's actually product in the sigma x eigenvector space. On the other hand, it looks like entangled if you just consider a sigma z, that is computational basis. Okay? So this shows this example, I mean simple examples warns us that जो दिखेगा वो नहीं भी हो सकता है, दिखने पे भरोसा मत करो. So there is a possibility it looks like entangled state, but it may not in other bases. So for example, to prove whether a state is entangled, that's why it's so difficult, because you have to find out, you have to search in infinite. So there is a numerical program now, probably one of the successful method now known till today in literature by Doherty, where he has written a program by which you can check that after certain iteration, you will be able to show whether a state is entangled. Of course, it can go to infinite. I mean, there is always a possibility, then you are gone. But it's a good numerical program. I mean, I know that is the only one successful numerical method exists by which you can check. So in mixed states, this is the problem that we understand already from two-party. Now mixed, for multi-party, things become more complicated. Now there is one small hint that I want to give to more complicated issues, so fully separable. Okay. Now suppose I have just three-party and I want to define biseparable state in case of mixed state. Okay? So you can think that you have three-party. Remember, I am defining biseparable state. Okay? So in pure state, you remember that what are the biseparable states? That is, AB is entangled, C is unentangled. Right? So you can easily say that one type of biseparable is that definition, or this is a example of a biseparable state in mixed state. Okay, it's just I extend it to a from a pure state to a mixed state, right? Clear? But this is not the definition of a biseparable state in case of mixed state, because you can also, so when you suppose I want to prove genuine tripartite entangled states in case of mixed states, then actually I have to show that rho ABC cannot be written in terms of PI this plus PI prime rho I AC tensor product rho I B plus PI double prime rho I BC tensor product rho I U. So you actually have to show a state to be a genuine multipartite entangled in density matrix when the state cannot be written in the convex combinations of all three. And of course you have to check in any basis. So you see, it is really, it's almost impossible. Okay? And this is exactly the case. So we still don't know a single computable measure which can characterize genuine multipartite entanglement in density matrix for arbitrary state. In case of pure, there are classifications exist. So let's rub this part. So in case of multi-party, I can also have pure and mix. Pure can be classified in different ways. So one is in a geometric way. This is known as geometric measures. And for mixed states, I really don't know any computable measure which can quantify entanglement content of a multipartite mixed state. There are several proposals. As I said, definition can always be given. We can sit one day class, we can devote to define one entanglement measure. Now the question is whether I can calculate for certain state. That's the hard part. Definitions can be found, but calculations is easy, difficult. So now the geometric measures I just briefly defined and end the class. So geometric measures were actually defined initially by Shimoni. Then there is a paper by Barnum and Linden in Physical Review A. Then there is a paper by Roy and Goldberg, PRA 2003. Then there is a paper by what is it? What? So these are the papers in which more or less geometric measures are developed. Still there are many open questions. This I talk only about pure states. So it's actually, you said that in the name, it's called geometry. So geometric measures are usually a distance-based measure. So logarithmic negativity is also a distance-based measure. Distance-based means it depends on some norm, either trace norm or any other norm. So whether they are a proper distance or not, that we are not going to discuss, because we know that any distance actually should follow some criteria. There are some follow, some doesn't. So these geometric measures, relative entropy based measure, they all are logarithmic negativity, they all are based on certain distance. So the previous logarithmic negativity is based on trace norm distance, and for example, relative entropy measure depends on the relative entropy distance. And now we will talk about other distance. So how it is defined? So any geometric, this measure of say psi a1, a2n is defined as 1 minus maximum of phi now phi belongs to some set S. Okay? Depending on the set S, it quantifies different categories of entanglement present in a multipartite situation. So what do I mean by that? If you have a fully separable state, that means that doesn't have any entanglement, because I have nothing I have done, right? Alice prepares A, Bob prepares B, Charlie prepares C, right? So this has no entanglement. So any entanglement measure that you define, it should give you 0. On the other hand, biseparable states is not really an entanglement 0 state, because it has entanglement in one of the bipartition. Okay? So I will choose the set S in my own will, and depending on that, this measure will characterize that kind of states. For example, this Y Goldberg has done that this S contains set of all fully separable states. Okay? That means the phi from which it will take the distance, this phi is of the form phi A1 tensor product, phi A2 tensor product, phi AN, right? This is the fully separable state. This is the measure that was defined by Y and Goldberg. Okay? So that means, according to the measure of Y Goldberg, if you take fully separable states, if you take the distance, you understand that if you take a psi as a biseparable state, it will be non-zero. Right? So according to their measure, G of psi, I am not putting A1, A2, AN, will be 0 for all psi which are fully separable, and G psi is non-zero or positive or non-vanishing for all state psi which is in say biseparable, in two separable to genuine. All such classes of states, it will be non-zero. Is it clear? Any problem, Jasleen? Sorry? Yeah, so what I said that you have to take a distance from the state which is given to you. So the state given to you is psi. So I want to quantify entanglement content of psi. I take a distance from phi. And the distance here is a kind of distance of Fubini study, or this is the fidelity based distance. Now phi, I perform maximizations over all choices of phi, and I choose the distance to be minimum, right? Because you know, when phi is exactly equal to psi, then it will be 1 and the quantity will be 0. So you take distance. Now, for example, if you have a fully separable state, you take the distance with that only, right? This is also allowed, and that will give you 0. Now I have a biseparable state, which is entangled in, suppose I choose something like psi is your psi AB tensor product psi C. This is biseparable state. Now I cannot take phi to be a biseparable because phi is all fully separable state, right? So I have to find a proper fully separable state which maximizes this distance. So surely this will give me some non-zero value. It will be not 1, different than 1. So that leads to a non-zero value of that G. Clear? Okay. So depending on the S, depending on the choice of S that you have, that's in your hand, dictate the value or dictate that what quantifications you want to make. Suppose I have a 4-party scenario. There is a fully separable state, there is a biseparable state, there is a triseparable state, okay, which is psi ABC tensor psi D type, right? So in case of 4-party, you have 4 kind, right? Suppose phi is fully separable, you know, there is a AB is to CD type entanglement. Then there is another state which is ABC is to D. Right? Suppose I now choose that S to be biseparable states. Okay? Then I only quantify triseparable and genuine multi-party entanglement, right? By G. So S is my choice. And you can easily see that suppose I choose something like this kind of state as my psi, and if my set is now biseparable, my phi will be exactly this. And I take an inner product that will give me 1, and so 1 minus 1 will be 0. So depending on the set S, I will be able to characterize G. Okay? Whether I can compute or not, again I repeat, that's a different story. Yes.
If I take S to be the set of biseparable states, then
It includes fully separable, of course. Because you know, biseparable are also fully separable. Whether you write A, B together or alag, same, no?
Will this ever be 1?
Sorry?
Will this ever be 1?
Actually, I mean, we can make it always scale it, but usually it goes up to half.
I mean, if you put a genuinely multipartition times it will go to half.
So now, in our paper, what we did is we called set of all non-genuinely multi-party entangled states. Okay? So, I mean, that means the states which is product in at least in one bipartition. Okay? We did not know whether people knew that this is actually paper of quantum capacity, but we define for a certain reason. And it turns out that if you choose the set to be like that, then this measure can be simplified enormously and can be computed for an arbitrary number of parties in arbitrary dimension. Okay? How? The proof I am not going to discuss. This is already in our this PRA paper, and later this was for 4-party because we require for 4-party. Then we realized that this proof is not known in the community because we were, you know, we thought that it is known, so we haven't written proof for arbitrary dimension. But then we have a paper with Onindo. This is a many-body physics paper, but we define there Prabhu. In Physical Review 8, 2000, I don't remember, possibly 14, where we prove for any thing. What happened? Can tell.
Nothing, it's just trivial.
Oh, good. But trivial in your case, maybe not trivial for me. So it's worth telling, no?
Definitely never, that subset is never going to happen.
Which subset?
Which is trivial for me is not trivial for you.
Oh, okay. No, that can happen.
Yeah, exactly.
Sorry?
nonsense.
No, come on. You will ask many questions I don't know. I have to tell. For example, I don't know what is multi-party mixed state entanglement measure. I have no idea. You may have after the class, right? You may try to define and give me a simple way to calculate. I will be the first person to be very happy because then many problems can be solved. Okay, so I'm not going to prove, but what I can tell you that if you actually change the set to be this, then G of, I think these many people know here in the class, because many people have calculated, this is nothing but 1 minus maximum of, and you can write in terms of the Schmidt coefficient. So any bipartitions you have choose for if you have a multi-party states of n party, you choose all the bipartitions, all the possible bipartition, and you calculate the Schmidt coefficient, you choose the maximum of that. There will be several. These maximizations can be hard to calculate, but then all these maximum Schmidt coefficient, you choose the maximum, then that will be that is the way to calculate this geometric measure, which we call genuine multi-party entanglement measure, generalized geometric measure, it's known. And so in case of 3-party, as you can see, this A and B consists of many A's and many B's, right? So what I called A is to B means all the possible bipartitions of A1, A2, An. Okay? So suppose you have make a bipartitions, I call this part A and the rest part B. Okay? Now you see that in case of 3-party, It just turns out to be 1 minus maximum of 3 eigenvalues. One is rho A, one is rho B, another is rho C. So if you calculate maximum eigenvalue of lambda rho A, maximum eigenvalue of lambda rho B, and maximum eigenvalue of lambda rho C, and you take maximum of all of them, that will give you the measure. Immediately in GHZ state, you know the local density matrix is half I. So these three are same, and it will be half. So 1 minus half is half. So immediately you get for n party what will be the geometric measure for GHZ. Got it? Now the obvious question comes as a homework, which is if you can calculate for W or any decay state. Okay?
So entirely the dependence of phi is gone.
Where is phi?
The state.
Yeah, that's the point. Actually, I mean, I can give you the hint of the proof. I don't know, have anyone proved this thing? You are supposed to prove, no? Great. Okay, so the proof actually goes, if you look very carefully, that if you perform measurements on, suppose a basis phi, I or something, okay? Because phi is the set, right? If you perform a measurement, then this is exactly the bond probability, right? Because if you perform a measurement in, say, phi clicks, then this modular square gives you the bond probability, right? That is the probability of obtaining outcome in a projective measurement. Now, entangled basis can give you a better value or can give you a better result, only helps you to prove that. Okay? There will be only few bipartitions which will be important, and then the entangled basis will help you to increase that, will give you the proof. And for pure state, it's just a Smith coefficients and done. So, proof is very simple. Okay?
Can there be a state which is biseparable but has more entanglement of formation than the genuine entangled state?
How will you define depends on that.
Using this measure?
No. Using that measure, of course not. Because you know that even for, you immediately see that it's for maximally entangled states. Okay. You know, it's actually maximally entangled state, it's also half, GHZ it's also half. So you can.
Let's say we have 3 qubits and it's a singlet state in first 2 qubits and a 0 in the third qubit. So we can make one.
You cannot make one because you have to be in a same scale, right? You cannot use a centimeter scale to quantify a inchy thing, right? So your unit should be same, right? You cannot say that the table's length is in centimeter and this is in inch. Then you cannot compare. So you have to be, when you quantify singlets, you have to quantify by a geometric measure, and same thing you have to quantify for a multipartite, right? Then you cannot.
I think you're asking about it might be that the GGM is same, but the UF different. Or
That
sorry,
is the
UF same, but the GGM is different.
That can happen. I mean, okay, hierarchy should not change. Okay, that is for sure again. So, you know, for example, logarithmic negativity and entanglement of formations for a given states, even a biparty, forget about mixed, I mean, you are going to multi-party. We know that they are different values, okay? But the point is whether it increases monotonically with entanglement, I mean, or whatever way, the same, these two, whether you characterize by logarithmic negativity or you characterize by entire formation, doesn't have any problem, because we know, for example, it will be immediately you can see even for pure state, forget about mixed. If you have a psi rho AB, the Entanglement formation is just von Neumann entropy of the local density matrix, has a completely different interpretations of thermodynamics. On the other hand, if you calculate logarithmic negativity, which is actually a distance measure, we know that this only can be determined by determinant of rho. We expect, because this is just, this may not have thermodynamic, you can find out some thermodynamic relation, that's a different story. But it should only depends on the eigenvalues, because it's a distance measure. It's a mathematical way to define. On the other hand, entanglement formation has a physical principle to define the von Neumann entropy. Okay? So there is a difference between the protocol-based measure, like disk level entanglement, entanglement cost, and the geometric way to define entanglement. Okay? What I want to tell that in one measure you see something, another measure you see, you cannot compare in that way. Only thing you differently, whether this only, for example, logarithmic negativity 0 and entanglement formation is non-zero cannot happen. Okay? In 2 cross 2. Always entanglement of formation and logarithmic negativity both will be positive in 2 cross 2 system. It's true that in case of higher dimension, due to bound entangled states, you immediately understand that logarithmic negativity will be 0. On the other hand, to create bound entangled states, you need entanglement. So entanglement of cost by definition of bound entangled state is positive. So they are different. Okay? On the other hand, again, disk level entanglement can be shown to be a lower bound of logarithmic negativity. So again, disk level entanglement 0 and logarithmic negativity 0 and disk level entanglement non-zero is not possible because it's a lower bound. Okay? So what I wanted to say that there can be a difference between the numbers, but numbers we should not believe. We believe on the characterization, means the overall characteristics, how it is increasing and things like that. Because they are mathematically, physically, everything is different. So they will give different values. We should not believe on the cover. We should go inside. Okay, so is it understandable, this GGM? So W state calculate and any decay state, can you write down a compact form? This is the homework for you people and submit. So the thing is that whoever crediting, all the homeworks that I am giving is the same rule. You have to write down the homeworks, you have to submit when you are submitting the assignment 1. And who are not crediting also can submit if Ratul is, if you give a treat to Ratul and just tell, like maybe you stop the video please, then I can